So, what if I told you there's this powerful problem-solving trick from computer science that can help you make better, faster decisions? Seriously, it's not about mapping out every single possible future. It's called the greedy method, and it's all about one simple idea: making the best choice you can see right now.
Okay, let's make this real. Imagine this. You've got a list of freelance jobs you could take on. You can't possibly do them all. So, what do? Do you grab the one with the biggest paycheck first? Or maybe the one with the deadline that's breathing down your neck? It's a tricky balance, right? And it's exactly the kind of puzzle where the greedy method just shines.
But hang on, before we dive in and solve that puzzle, we need to get our heads around the philosophy here. Let's break down the key concepts that really make the greedy method work.
First up, we've got this idea of a feasible solution. All this means is that for any problem, there are usually a bunch of different answers that technically work. They follow the rules. In our job example, any schedule of tasks that you can finish before their deadlines, well, that's a feasible solution. They all get the job done, so to speak.
But, just because a bunch of solutions work doesn't mean they're all equal. Somewhere in that sea of possibilities, there's one that's the absolute best of the best. That's what we call the optimal solution. It's the one perfect outcome. In our case, the schedule that makes you the most money. Period.
So how do we even measure what's best? That's where the objective function comes in. Think of it like a ruler we use to judge every possible solution. We're either trying to maximize something good, like our profit, or we're trying to minimize something bad, like our costs. It gives us a really clear target to aim for. And this brings us to the secret sauce. The greedy method doesn't sit around and overthink every possible future. Nope, it just makes the choice that looks best in this exact moment, based on that objective function we just talked about. It's a simple step-by-step approach that gets you to a surprisingly good solution, incredibly fast.
Okay, enough theory. Let's put this thing into practice. We're going to go right back to that opening puzzle about the jobs and see exactly how a greedy strategy can build us a schedule that maximizes our profit.
For this problem, our greedy rule is about as straightforward as it gets. We always deal with the most profitable job first. We're just going to let the money do the talking and go for the biggest payouts.
Here's how we do it. First things first, we take our list of jobs and we just sort them by profit, from highest to lowest. So J1 goes to the top with its profit of 100. Then comes J4, then J3, and poor old J2 is at the bottom. This sorted list, that's our game plan.
All right, now let's build the schedule. And here's the little trick. We try to place each job in the latest possible time slot that still works for its deadline. This keeps the earlier slots free for other tasks. So we grab our number one job, J1. Deadline is 2, so we slot it into time slot 2. Perfect. Next up is J4, deadline 1, so it has to go in slot 1. Now, J3, its deadline is 2, but slots 1 and 2 are already taken. There's just no room, so we have to say goodbye to J3. Finally, J2 has a deadline of 3, and look at that, slot 3 is wide open. It fits right in.
So, what's the grand total? After making those quick, greedy choices, we scheduled jobs 1, 4, and 2. And that nets us a total profit of $137. Not bad, right? That's a fantastic outcome from a really simple step-by-step process.
But the greedy method is no one-trick pony. It's not just for making money. It is incredibly versatile. So let's look at a totally different kind of problem. How do you build the cheapest possible computer network? This is also known as finding a minimum spanning tree.
Now the rule changes, but the core philosophy is exactly the same. Our new greedy rule is this: always add the connection, or what we call an edge, that has the lowest cost. There's just one tiny catch: we're not allowed to create a closed loop or a circuit.
So here's our network map. Each one of those circles is a point, or a node, and the number on each line is the cost to connect them. The goal is super simple. Connect every single node together, but do it for the absolute lowest total cost possible.
Okay, let's get started. We just scan all the possible connections and greedily snatch up the cheapest ones first. So the 2 edges with a cost of 2? Yeah, those are a no-brainer. We add them. What's next? The edges with a cost of 3. Let's add those 2. You see how we're slowly building this thing out, one cheap connection at a time?
And here is where that no loops rule becomes so important. The next cheapest edge costs 4, but look what happens if we add it. It creates a closed triangle. That's a loop, so we have to skip it. Same thing for the edges that cost 5 and 6. Adding them would also create circuits, so we greedily reject them. Finally, that edge with a cost of 7 connects our last point, and bam, the network is complete.
Just think about what we just did. By just making a series of simple what's best right now choices, literally just picking the cheapest edge that didn't break our rule, we built a full network for a total cost of only 17. I mean, that's the power of greedy thinking right there.
Now, this all seems pretty awesome, doesn't it? It's simple, it's effective, but there is a really crucial trade-off we have to talk about, and that's the constant battle between being fast and being absolutely perfect.
Let's compare the greedy method to something else, like a divide-and-conquer strategy. A greedy algorithm is just blazing fast. It makes a choice, and it moves on. The trade-off? Well, it aims for that perfect optimal solution, but there's no guarantee it'll get there every single time. What it does guarantee, though, is a pretty darn good solution, and it finds it fast.
So, you might be asking, why would we ever use an algorithm that isn't always perfect? Well, because in the real world, good and fast is often way more valuable than perfect but slow. Let's take a look at where this kind of thinking pops up.
You know that minimum spanning tree problem we just solved? That's not just some abstract puzzle. It's used everywhere. I'm talking about designing telecommunication networks to use the least amount of cable, helping computers process images by grouping similar colors, mapping out evolutionary trees in biology, even analyzing social networks to find key connections. This greedy approach gives us real, practical solutions to incredibly complicated problems.
And that kind of leaves us with one last thought, one that goes way beyond computer code. In our own work, our own lives, it's really worth asking, when is the endless search for a perfect solution tomorrow actually stopping us from getting a great one today? Sometimes, the smartest choice you can make is the greedy one. Thanks for tuning in.